Okay, so these are some problems involving a polynomial ring where the coefficients are coming from a field, that is f is any field, and we are also assuming that the zero polynomial has degree -1. We are defining its degree to be -1. Now we have to determine that in each of these cases whether the set forms a ring with respect to the operations in fx, that is addition and multiplication of polynomials. Okay, so let us see how we can solve this problem. When you want to verify that a set is a ring with respect to two operations, first of all the set has to be non-empty. Okay, so that is one condition. The second thing is that if the elements of the set are coming from some known ring, in this case that's the situation. We already know that fx is the set of all polynomials with coefficients from f that forms a ring with respect to addition and multiplication of polynomials. Now from that ring only we are considering elements. So this is actually a subset of fx. We want to prove that this subset also forms a ring, or we want to rather see whether this subset forms a ring with respect to the same operations that we have in fx. In other words, we want to see whether this is a subring of fx. So clearly, if it is to be a ring, then its zero element should be the zero element of fx, because it's a subset of fx and the operations are also coming from fx. So if at all it's a ring with respect to those operations, then the zero polynomial should be here. Okay, but you can see that the zero polynomial is not here. Here we have those polynomials whose degrees are equal to 0, namely all non-zero elements of the field f. Since degree of 0 is defined to be -1, so 0 does not belong to this set. So you can write, since degree of 0 is equal to -1, we have this. So the set does not form, if the zero element is not there, then clearly it cannot form a ring. Does not form a ring with respect to the operations in fx. Okay, so that is number 1. Number 2, in number 2 the set consists of those polynomials f whose degrees are all equal to -1. Now we know by the definition of degree of a polynomial that if f is a non-zero polynomial, if f is something other than the zero polynomial, then its degree is defined to be the exponent of the largest possible exponent where the corresponding term has non-zero coefficient. For example, what we mean by that is this: say you have 2 plus 3x plus x square. Then in this polynomial, say this is a polynomial in fx. In this polynomial, the largest exponent for which, the term in which the largest exponent is appearing has a non-zero coefficient 1. So the degree is 2. Degree of this polynomial is 2. Okay. If in place of this, if you had this polynomial, say 2 plus x, then the largest exponent that is appearing is this. Note that exponent 2 is also present here, but it's present like this. And for that matter, exponents 3, 4, 5, all those exponents are present, but they appear in terms where the coefficients are 0. We have to consider the largest exponent such that the term in which it is appearing has non-zero coefficient. Here the coefficient is non-zero 1. So its degree is equal to 1. And because of that same reason, if you take just a scalar, say 3, then it is a term that looks like this. So the largest coefficient, the largest exponent appearing in this with a non-zero coefficient in that term is 0. So this is equal to 0, and that's why every non-zero field element, when viewed as a polynomial, has degree 0. However, because of our special definition of the degree of 0 to be as -1, this set will have only the 0 polynomial. Okay, so that is why note that the given set any non-zero polynomial has a degree that is a non-negative integer. The only negative degree is -1, and that is of the 0 polynomial. So this is equal to 0. So this clearly is a ring with respect to addition and multiplication of polynomials. It has only one element. It's the 0 ring. Okay. Hence, the set in this case is a ring with respect to the operations in fx. You may wonder one thing. I wrote this polynomial, right? 2 plus something like this, 2 plus 3x plus x square, and I said that it's a polynomial in fx. You may wonder that f is a field. F can be any field. So in any field, what is the meaning of 2, 3, etc.? For that, you go back to the definition of a field, and there you will see that in a field we always have the multiplicative identity 1. By 2 we just mean 1 plus 1, by 3 we mean 1 plus 1 plus 1, and so on. And one more thing you note, that in a field, in the definition of a field, 1 is always not equal to 0. In a general ring, that's not the case. In a general ring, you may have 1 equal to 0, and that is precisely when the ring itself has only one element, 0 element. But when you come to a field, there the multiplicative identity and the additive identity are by definition different. Okay, so these are non-zero. This is non-zero. This, however, we don't know. If the field has, say, 3 elements, then this 3 will be equal to 0. Such things are possible, as you may already know, in finite fields. Okay, so in this case, it's a ring. And the third one was this. So 0 minus 1, then so this is 3. Let me write 3 here properly. Degree of f equal to minus 2. Now, by our definition of degree of a non-zero polynomial as well as the zero polynomial, degree is always greater than or equal to minus 1. So, degree is never equal to minus 2. So, no polynomial is there in this set. So, this is the empty set. Hence, an empty set definitely cannot be a ring with respect to any operation whatsoever. Hence, the set in this case is not a ring with respect to the operations in fx. Then number 4. So in number 4 we have those polynomials whose degrees are all less than or equal to 4. Such that degree of f is less than or equal to 4. But if you take the product of these two polynomials, then it becomes x to the power 8, which does not belong to the given set. So the given set is not closed with respect to multiplication, and hence it cannot be a ring. When you come across a set like this, you have to be able to see beforehand, I mean even before solving the problem, you have to guess whether it's a ring or not. You just quickly look at whether 0 element is there. If it is there, then you proceed further. If 0 element is there, then next you see whether the set is closed with respect to addition. Then you see, if that is true, then you see whether the set is closed with respect to multiplication. Does the set have negatives of all the elements in the set, negative polynomials? I mean, for a polynomial f, whether minus f is also there in the set. If all the things continue to be true, then you can start showing that it's a ring, it's a subring of fx. If one of the conditions fails, then there itself it stops, it cannot be a ring. So here, for example, you can see that since degree of f has to be less than or equal to 4, so the 0 polynomial is present here, its degree is -1 and -1 is less than 4. Now if you take two polynomials, any two polynomials, each one has degree less than or equal to 4, then their sum will have degree also less than or equal to 4, because for example you can take two polynomials, one say this one, x minus 2x square plus x cube, this is one polynomial, and another polynomial is say x to the power okay, let me just write it in that sense where the exponents are increasing, x minus 2x to the power 4, and you take their sum, then the sum, whatever terms come here, you will always have a term with the highest degree. So that will continue to contribute to the degree of the sum. I mean, you can see x plus x will be 2x, but we are not really bothered about those lower degree terms. We have to look at the term having highest value of exponent with non-zero coefficient. So this polynomial has degree 3, this one has degree 4, and the sum has degree 4. So when you take the sum of two polynomials, the result is it will not exceed 4. If you had 2x to the power 4 here, then the degree will get reduced, the degree will be 3, but it cannot be 5 or 6. That is not possible when you are talking about sum. But when you take product, there only degree increases. I mean, there is a chance for the degree to increase, and that's what happened here exactly. So in an order to show that things go wrong, we considered a product with as much degree as possible. So we considered x to the power 4 times x to the power 4, that gives us x to the power 8. Now this is a polynomial of degree 8, so it cannot belong to this set, and as such the set fails to be closed under multiplication, and this in turn tells us that it cannot be a ring. So in this case the set is not a ring. Under, you can write with respect to or under, they mean the same thing. Under the operations in fx. Okay, then number 5. In number 5, we have the set of those polynomials whose degrees are non-negative. Degree of f is greater than or equal to 0. And that set clearly will not have the 0 polynomial because its degree is negative, -1. Note that the 0 polynomial in fx does not belong to the set so the set in this case is not a ring under the operations in fx. So this also fails to be a ring, but for a different reason. Here we had the zero polynomial, still it failed to be a ring because it's not closed under multiplication. Here we don't even have the zero polynomial, so we need not go any further. Number 6. In number 6, the set is this. It is the set of all polynomials in fx such that degree of f is greater than or equal to 1. Now by our definition of degree of a polynomial, it's always greater, any polynomial has degree greater than or equal to 1. Equal to 1 only when the polynomial is 0. If it is non-zero, degree is strictly greater than 1. It's non-negative. So that's why this is the entirety of fx, and we already know that fx is a ring with respect to addition and multiplication of polynomials. Addition and multiplication of polynomials. Then number 7. Okay, in number 7 we have degree of f such that this is rational. Degree of f is rational. Okay, in this case also the set is the entire fx. That is because the degree of f, the way we have defined degree, for any polynomial the degree is rational. In fact, it is an integer. So that's why this is equal to fx. So in this case also it's a ring. Okay, I am not repeating that again. In this case also the set is a ring. And finally we have 8. Here the set is, for ease of writing, let us name it. Let's call it A. degree of f is even or minus 1. Okay. Note that 0 belongs to A. Its degree is minus 1, so 0 will belong to A. Our aim now is to show that this is actually a ring with respect to addition and multiplication of polynomials. Let f and g be two elements in A. Then so cases will appear. If at least one of these two polynomials is 0, then clearly their sum belongs to A. Why? If f is the 0 polynomial, then this sum is g, okay, which is already there in A. If g is the 0 polynomial, then this sum is f, which is also there in A. If both of them are 0 polynomials, then their sum is the 0 polynomial, which is also in A. So if at least one of them is the 0 polynomial, then the sum is automatically in A. Assume that they are both non-zero. If they are non-zero, then their degrees cannot be equal to minus 1. So, but they are at the same time in A, so that means both of them should have even degree. We could have worked with multiplication also here. Okay, we will see that later. And then degree of f and degree of g are both even. This implies degree of f plus g. Oh, we claimed that this is a ring. Now I think it's not necessary for it to be a ring. Okay. No, this will not be a ring. I thought the evenness will force it to be a ring. I guessed it incorrectly. See, I also did not know. I thought it would be a ring, so I was proceeding to show that it's a ring. But now suddenly I realize it will not be a ring. Let me tell you the reason for this realization. This polynomial as well as this polynomial, they are both in A, right? Because each one of them has degree 2. But if you take their sum, what do you get? You get 2x, which is a polynomial of degree 1. Since 1 is odd, this sum will not be in A. So A is not closed under addition. So it will not be a ring. So we can provide this example itself. It's not necessary that right after looking at the problem you will immediately guess the correct answer, but when you do it you have to modify the solution. Note that x plus x square and x minus x square both belong to this set. But their sum does not belong to the set. So in this case the set is not a ring under the operations in fx. Okay, that part is understood. So these were some sets of the type that you mentioned, which is to be verified whether it's a ring or not under addition and multiplication of polynomials. Many such questions we will encounter, and their solutions also we will try when we study polynomial rings. It's coming. We haven't touched on ring theory for quite some time, but we will go back to ring theory once this current set of exercises on groups is over, and which will be over soon. So there in one section we have polynomial rings. So there we will see many different types of problems, not only these problems but many other types of problems. Namely, for example, if a polynomial over a field is given, how to say whether it's irreducible, or for example, if a how to put it in words, I forgot the exact phrase, what I was trying to say. Oh yes, fields with finitely many elements. If you look into field theory deeply, you will know that the finite fields, all of them have orders of this form, p to the power n, where p is a prime number and n is a positive integer. All fields have orders of this form. You will be asked to construct a finite field with so and so order, say order 8 2q or order 16. In carrying out those constructions, we can take the help of polynomial rings and irreducible polynomials in them of some particular degree. Okay, so those things we will see in those parts. So I end the video here today. If you have any other queries, you please let me know in the comment section. So with that, I sign off for tonight. Have a nice night.